and she's been doing very interesting work on fair machine learning. Some of this work was recently a best paper winner at ICML. And I think, did you give the talk there?
Yeah.
Yeah. But she's going to give us some introductory material at the beginning as well. So thanks.
Thank you. Yeah. Okay, thanks everyone for coming. So I'm going to talk about our recent work, the delayed impact of fair machine learning. So this is joint work with Saradin Astarov, Maxim Kowitz, but also PhD students in the computer science department and my advisor, Moritz Hart. So I guess many of you might be kind of wondering why we're talking about fairness in a class that you sign up for that's called Special Topics in Deep Learning. And it is a fair question because no part of this talk is going to be specific to deep learning. So I'm not going to talk about, actually I'm not going to talk about deep learning at any point in the talk. But so the larger topic of fairness in machine learning, though, has become a topic that all machine learning researchers are increasingly concerned about. And so many of these things is not just applicable to one method of machine learning. It's like a problem that is we see in all kinds of machine learning, including deep learning. So maybe I hope to in this talk, give some introduction to the ways people reason about fairness problems in machine learning. So if you look at the history of studying fairness in machine learning, it's kind of recent. So a lot of the work that has come out of fairness has really increased in the last couple of years. And now, not to scare you off, there are at least like 21 different definitions of fairness for algorithms that people have come up with. So I'll refer you to this tutorial by Arvind Narayanan earlier this year, where he introduces all these fairness criteria. Now there are probably more than 21. And so this should not be surprising to you because fairness as like a human concept has been something that philosophers, economists, like political scientists have tried to grapple with for like hundreds of years. And it doesn't make sense for computer scientists to think that there should just be one or two criteria that can fully characterize what fairness means. So in a sense, having a lot of definitions is not something that should be surprising or weird to us. But so I will first want to maybe introduce some of these fairness criteria that is more that has been talked about more in the literature. So first, so here's the brief introduction to actually like 3 fairness criteria that are part of a class of fairness criteria that we call observational fairness criteria. So there are many fairness criteria that are not necessarily observational. Here we'll kind of talk about them first because it's something that we talk about in our work as well. So for observational fairness criteria, there are also many definitions. And there are some things that we'll talk about today that is, we'll mostly just talk about the definitions today. So just to recap the typical setup, we're in this classification setting where you have access to features of an individual. And in particular, there's one feature called the sensitive attribute, which might be the race or gender associated with the individual. And we kind of want to be fair with respect to this sensitive attribute. And now we assume there's a classifier that maps all the features, so X and A, to some prediction. And the variable we want to predict is Y, which is the actual outcome. So all this is in a familiar classification setup. And all these are all random variables, and they're in the same probability space. So here we'll just denote the conditional probability when we condition on the group attribute. So A, I will just refer to it as the group attribute or the sensitive attribute. So the probability distribution conditioning on the group attribute would denote it with P sub A. If that notation comes up, that's what I mean. So here's the setup. But a lot of the time we forget that the setup is a very, very fragile abstraction for what is happening in the real world. And maybe this is something as machine learning researchers we don't always talk about. But all this is also very central to the issue of fairness. So first thing is that the feature matrix that we have, it contains all sorts of measurement biases. We assume that usually for modeling, we assume that our data is sort of accurate, and sometimes we just take it as given. But then if we're thinking about demographic surveys, a lot of the data that we get are from very imperfect measurement tools. And then the sensitive attribute that we're hoping to be fair with respect to, that is sometimes not even known, right? For example, sometimes this is it could be a missing cell in your data matrix. Like, for example, I want to be fair with respect to race, but some people don't even report their race, right? So this is also a problem. And so when we talk about this classifier that we want to make it fair, it might not be a single model, right? It might be the result of a composition of a lot of different models. A lot of things can happen in this long machine learning production pipeline. And we're kind of just abstracting that into a single classifier. And also Y also has problems. It might be a proxy for what we are actually interested in, right? Maybe we are predicting, so some of these examples will come up later on. Okay. So what is an observational fairness criteria? So the definition for observational fairness criteria is kind of intuitive, right? It is something that we can specify using the joint distributions of all the random variables we talked about, x, a, c, and y. So anything that we can write down as a probability statement involving these objects, we call that observational fairness criteria. But if you're writing down, if you find yourself writing down another random variable that is not is not measurable with respect to this probability space, then that's no longer observational criteria. And now with this setup, we can ask some questions about the observational criteria. And so because there are so many different criteria, one is whether we can achieve them. Another question that people have tried to ask is how do these criteria trade off? So there are some impossibility results on how you can achieve one fairness criteria, but then that gives you no hope of achieving another fairness criteria. And all these things come up in public discourses about which criteria should we legally require from algorithms. And this is a matter of ongoing debate. So, so the first criteria we'll talk about is demographic parity. So demographic parity just means that for all the groups have the same rate of being classified positively, right? So we can frame this as an independent statement, which is the classifier is independent of the group attribute. But we can also write this as a probability statement here, right? So if C just binary 0, 1, we're just saying that the probability of positive classification is the same across all groups, right? And this seems pretty reasonable so there are also approximate versions where you relax that strict inequality, right? So it sounds reasonable until you think about how one might try to achieve demographic parity. So one way of achieving it when you have a classifier that does very well for group B, so you are able to select qualified people in group B, but then it does very badly for group A. Then how do I make it satisfy demographic parity? You can just do whatever it was doing on group B, but then in group A, I will just, for example, it was selecting like 50% of the people in group B, right, who are qualified, and then in group A, I can just say I randomly select 50% of the people. And now my classifier satisfies demographic parity because it's selecting 50% of the people for both groups. But then in group B, it's selecting qualified people, and in group A, it's selecting random people. And that does not strike you as fair, hopefully.
Are you defining qualified?
Yeah, so for now, let's just think of So qualify, we also define it rigorously. So by qualify, I mean people who actually have ground truth outcome y equals 1, right? So if it's qualify if you know they're actually a true positive. Does that answer your question?
You said you're going to talk about it more, like in the.
Yeah, it'll come up again.
Okay.
Yes.
So you said that selecting random people wouldn't be fair. Did you qualify what fairness was in terms of selection, or?
Yeah. So okay. So I think one of the things that you notice in this talk is that there's no one idea of fair, right? So basically, I want to be saying that when we are fair with respect to demographic parity, there are also some pathological situations that you will intuitively think as a bad thing to do, right? And that is something that this fairness criteria allows for. But then to formalize what we think is wrong about this pathological situation, we need to formulate another fairness criteria, right? And this kind of thing kind of repeats because we find that no one fairness concept, you know, that we can frame as a parity statement is sufficient to encapsulate all we think should be, you know, should be done by a fair classifier. So, right. So this kind of thing can happen if I have very little training data in group A and a lot of good training data for group B, so I just become lazy for group A and call it a day, which is something that we think, hopefully you also agree, is bad. But then another problem is that the perfect classifier, where you have an oracle for the outcome and you just predict the outcome, is actually not fair according to demographic parity, because if the base rates are different, right? So if your base rates are different, you just, even your perfect classifier has different rate of positive classification for different groups. So somehow that just can never be fair in that case. And this also seems like a problem. So then what about some other criteria? Can we define something else that maybe goes around these problems? So one thing that seems reasonable, again, is that you have the same error rate across all groups, right? And this seems like a good thing to enforce. So when you have you enforce equal error rates for all groups, then you encourage the person who's building the classifier to actually go out and find more data, right? If it was lacking data in a certain group, so it actually incentivizes them to improve the classifier for all the groups. So this kind of works around that. And it also allows the perfect predictor, right? Because the perfect predictor just has 0 error rate for all groups, and that's fine. But this is also not exactly perfect, because now we're saying you just need to have equal error rates. But what if we are making different types of errors for different groups, right? So for example, so just now we talked about qualified, right? So there are essentially 2 types of errors that we're interested in, right? So false negatives, which is where someone is actually has y equals 1, but you output c equals 0, right? And that's false negatives, and that means you rejected a qualified person, right? And then there's also false positive, which is the actual outcome is y equals 0, you predicted c equals 1, so you are accepting unqualified people. So now if you have different error rates for the 2 gender groups, then instead of saying I want to reject less qualified women, you can say I just increase the error rate for men, and then by accepting more unqualified men. So now I have equal error rates. But that seems, again, like a pathological way to achieve that accuracy parity. And now this kind of hints that we need to look at different error types, right? And this especially matters if there's outcome asymmetry, where there's a positive outcome where people, there's an obviously good positive outcome, right? In this case, if the good outcome is getting loans, you want to make sure that you care more about making sure that qualified people get loans versus the other kind of error, which is the false positive error. Yeah, so this brings us to another criteria, which we call true positive parity. It's also referred to as equal opportunity, which I'll use the term equal opportunity in the second part of the talk. But in general, this gives us a way of distinguishing between error types. So now this statement here is saying that given that my true outcome is positive, my rate of actually predicting positive is the same for all groups, right? And this probability that I'm writing here is the true positive rate, right? And that's why it's called true positive parity. And then, that, like I said just now, it makes sense if to consider particularly the positive outcome if it's desirable, right? And so again, we can also say, you know, if now the negative outcome is the one that's desirable, then I want to impose false positive parity, right? So I want to make sure I don't, you know, I want to make sure the mistakes of this type are the same for all groups. And then if I satisfy both true positive parity and false positive parity, I call that satisfying equalized odds. And that basically means that that equalized odds is a conditional independent statement, because I'm saying condition on my outcome. Now my classifier is independent of the group, right? Because conditioning on the outcome, the classifier's probability of classifying positive is the same for all groups, right? So I condition on y equals 0 or condition on y equals 1. So this would be like a brief introduction into some of the observational fairness criteria, and it will be sufficient for the rest of the talk. Yes. So all the criteria that I talked about just now, as well as many of the other criteria in this 21 list, they can be achieved using efficient algorithms. And you know, there are forms of achieving this using post-processing. So you can just train a classifier / predictor and adjust it after that, or you can append something to your loss, so to correct for fairness during training. Or sometimes there are some fairness criteria where you can just do plain empirical risk minimization and you already get bounds on your fairness satisfaction. So something I alluded to just now is that it's impossible to satisfy these fairness criteria simultaneously. So then that has been sort of well discussed in the field. What we now I want us to kind of turn our attention to, like, what are we hoping to do with all these fairness criteria, right? And yes.
So if you wouldn't mind me asking, it looked like the last criterion was stronger than the others, or at least no, that's not right. But it looked like correcting the condition distributions was stronger than the positive or negative. I guess the demographic parity is too strong, right? Isn't there a simple ordering of these things, or? No. So I think for in the case of these two, you can satisfy one but not the other, but you can satisfy the other but not the first one. So it's not a strict hierarchy. Yeah. Okay. But maybe we can talk about this later. Yeah. So one of the things that you know, we repeatedly bring up is the idea of harm, right? And then somehow when people propose new fairness criteria, they're hoping to prevent certain kinds of harm. So why are we not really talking about where the harm is coming from, right? So then the question that we started thinking about is it true that when machine learning systems are fair with respect to these fairness criteria, that means you know, our protected groups, by protected groups I mean, you know, a group that has a particular sensitive attribute, are they better off because we applied the fairness criteria? And so this is something we want to critically examine, because it seems to be, you know, the assumption that fairness is going to prevent some kind of harm. And it's important if we know it's true or not. So before I talk about this, I want to go through a simple example with credit scores. So I guess people here are familiar with the idea of credit scores. Is something that predicts how you know, credit worthy you are, and you know, how likely you are to repay the loan if your loan application is approved. So here I have two groups, a blue group and an orange group, with different distributions over their credit scores.
right? And then the higher your score is, the greater the proportion of people who would repay their loans, right? So the solid circles indicate like the proportion of people who would repay, and then the empty circles indicate like the people who would not. But you don't a priori know who will repay or who will not repay, you just know the proportion, right, at each score. So given this, I want to say that the blue group here is our protected group, and we want to kind of check if our procedure is being fair to this group or preventing them protecting them from some kind of harm. So if we use one of the fairness criteria we saw just now, which is demographic parity, we are making sure that the proportion of people we approve for loans is the same for both groups, right? So that gives that when we apply that ends up giving us these these thresholds here, and then we approve the loans for people whose scores are above the respective group thresholds. And then after they get their loans, their scores will change, right, according to whether they repay or they default. So people who repay their loans, they would have higher credit scores. If they default, your credit scores will take a hit, right? And what has happened here with the orange group is that all the people who've gotten loans have repaid them, right? And the scores got better on average. And for the blue group, some people repaid their loans, but more people defaulted on their loans, right? So their scores actually got worse on average. So what has happened here is that when your scores get worse on average, that means you have less access to credit in the next time step, right? You have more debt on average in the next time step. So that is something we can reasonably agree that is a harm, right? And then what I showed you with this example is that fairness criteria didn't seem to help the protected group, right? Once we considered the impact in the next time step, right? So the downstream impact of this classification that has happened here. So what we do in this work is we go through the same kind of analysis for what is the downstream impact, or what we call the delayed impact of applying fairness criteria. And we do that by introducing a general tool called the outcome curve that allows us to describe the quantitative impact. And then using the outcome curve, we are able to provide like a complete complete characterization of the delayed impact for 3 different fairness criteria, some of which we talked about just now. And in doing so, we showed that when you apply fairness criteria, there are a large class of settings where applying the fairness criteria actually causes harm to the groups that you intended to protect with the fairness criteria. So this tells us that if you don't yes.
So I guess were you about to finish this point, or I wanted to ask about this problem setting, like your assumptions and stuff. But I mean, I guess
yeah, it's going to come up in the next slide.
What?
The problem assumptions. But do you have a specific question?
I mean, I guess if you're talking about the assumptions, yeah, because I mean I wanted to bring up something I thought about when I was reading the paper, but
sure.
You can, I guess.
Okay, cool.
If it makes more sense in a second, yeah.
Yeah. Yes.
And so on the graph, once you've selected who's receiving loans, and then the people who default get shoved into lower credit scores, and people who don't get shoved into higher credit scores, does the placement of a person within the credit score affect the ability for them to pay back their loans? Or are there always just going to be distribution of people that can't pay back their loans and they're just shifted around on the credit score graph?
Okay, so I think if I understand your question correctly, we do have to assume that the credit score actually is monotone in the repayment probability, which will come up in the next slide.
Okay.
Yeah. So hopefully this will clear up some of the problem setting questions. So formally, right, the score here, that we talked about, it's a scalar random variable, right? That is a function of the individual's features. So the credit score, it's an integer valued random variable. And if an individual has a credit score, then any group of individuals has a particular distribution over the scores, right? And so, it's reasonable, or in fact, if we have a score, we hope that the score indicates that individual's success probability, right? So
formally, we want to state that as the monotonicity assumption, which is when you have higher scores, that means you're more likely to repay.
Okay, yeah, this is what I was wanting to ask about. Isn't it possible? I mean, so we all know that when you have a lower credit score, you get a higher interest loan, which, you know, is strictly speaking harder to repay because you have to pay more money.
Mm-hmm.
So aren't you kind of overlooking the causality, like the, you're saying, you know, okay, the score predicts how far you know, whether you can repay the loan, but isn't that also, I guess it seems like there's you know,
yeah, that's a good point. That's a good point. So so here we are looking at identical loans, and that's why we're not taking into account you know, that maybe there's an additional effect, right? So here we're just saying that, you know, where we want to study this simple case where your probability of repayment is actually monotone in your score. And this is something that it looks like a strong assumption on paper, but it's something that we actually see in empirical distributions. So I guess maybe you know, something like taking into account the interest rates isn't actually a strong enough effect to change the monotonicity assumption.
So I didn't see this when I read the paper. I didn't see whether you had the interest rate on the loans in the FICO data, whether it was, I guess.
Yeah, let's talk about that when we get to the experiments.
Okay.
Yeah, okay. So when we have these scores, you know, we have to choose. So the classification problem becomes a problem of thresholding the scores, right? So we pick the threshold. In fact, the bank picks the threshold to maximize their own expected utility, which is in this case the profit from giving the loans. So that would be the sum of the expected rewards from people, the repayments, and subtracted the expected loss from the defaults, right? And the expectation is taken over, you know, the randomness in the population distribution, right? And then for any particular group, by picking a threshold t, you know, that means we are selecting a beta proportion of that group. So for any particular group distribution, there is a one-to-one mapping between the threshold we select and the acceptance rate for that group, right? And we can say that the decision variable for the institution is the threshold. We can also say that the decision variable is the acceptance rate. And when there are multiple groups, of course, this is not true in reality. We cannot have credit score thresholds that are group dependent, at least now under the current law. But then if we apply some of these fairness criteria, that essentially forces us to choose group dependent thresholds. So we allow group dependent thresholds in this case. So just a recap of what we already said, when the scores of the accepted individuals repay or default, their scores will change, right? And here we assume that the scores for the not accepted individuals do not change. And then the average change in score for each group is what we call the delayed impact. And we use that to basically summarize the change in the distribution of the scores at the population level. So under the mild assumption of monotonicity, we can characterize the shape of the delayed impact as we change the acceptance rate for a particular group. So this is a concave function. And so this is what I'm plotting here with on the graph as well. So on the x-axis, we have the acceptance rate, and on the y-axis, that is my delayed impact or the average change in score for that group. So if the bank, you know, can choose to give out loans to everybody, or you know, it can also choose to give out loans to nobody. So that's 1 and 0. And when you're not giving out any loans, then you have no impact. You know, there's no average score change, right? The average score change is just 0, so that's where the curve starts. And if you tell the bank to do whatever you want, the bank might say, I want to maximize my profit, so I would choose the acceptance rate that maximizes my profit, right? And that's beta max utility. And so beta max utility gives us a particular average score change, right? And so the question is, you know, is that where is beta max util? So it turns out that, you know, with a simple assumption that is realistic, for example, in this credit setting, which is that the banks have disproportionately high harm from default compared to the harm individuals experience when they default. So that pushes the bank to be more conservative in giving out loans. So it would give out loans to people who are profitable, but it will exclude some people who are likely to repay their loans, but are no longer profitable, right? So that's what I mean by beta max util is actually happening before the maxima of this average score change curve, right? And then so at this point, the bank can choose to give out more loans, right, to people who are still likely to repay but were not profitable to loan to. So that can still increase the average score change further, right? And then we call this blue region where we are increasing the average score change beyond beta max util. We call this relative improvement because you're improving the average credit score beyond just naive utility maximization. And now, now the curve has peaked, and after we call this point where you are maximizing the positive outcome, philanthropic optimal, right? Because this distinguishes the max util from what is maximizing the average score change. And then if the bank has gives out even more loans, then you have to give out loans to people who are less likely to repay, and that's going to pull down the average score change. Up to a certain point where we are again at the same level of delayed impact, right, as under max util, right? So we consider the delayed impact achieved at max util as a baseline point. So when we are experiencing a lower, less positive delayed impact than the max util, we call that relative harm. And then at some point, you're giving out so many loans that you have to give out bad loans. You have to give out loans to people who are most likely to default, right? And that really pulls down your average credit score in that group. And then we call this particular regime where the score is actually going down, we call that active harm. So now I've just introduced like 3 regimes of interest that might quantitatively and qualitatively tell us what is the nature of the delayed impact of this loan policy, right? You can either cause relative improvement with respect to utility maximization, or you can cause relative harm, or in the worst case, you can cause active harm. And the question is, when we apply fairness criteria, which of these 3 regimes do we land up in? Yeah.
So this graph is for like a disadvantaged group in the population. With respect to like where max util is being placed?
Yeah, max util, yeah.
So if we graphed the population as a whole, including both groups, where would max util be placed along like this hump?
Yeah, it will still be before the hump. Yeah, this is general. So the now I mean we can think of us as we can think of this as being a protected group, but you can also think of this as just any other group, and the shape is the same.
So, okay, the way I'm thinking is the bank, if higher credit scores throughout the population translate into more profit for the bank, so wouldn't the bank's policy be to maximize the average credit score increase of the entire population to maximize its profit?
Yeah, so the problem is when you have the banks. So when the bank suffers, a default, right? It's because its default is relatively larger compared to its loss from a default is relatively larger from the amount your credit score decreases when you default, right? That's why it wouldn't just accept everyone whose credit score is expected to increase. It will only accept everyone whose credit score is expected to increase beyond a certain amount, right? If my expected score increase is 0, my expected profit is actually negative.
Are you assuming that the only loss that the individual suffers is a decrease in credit score and not like their house being repossessed when they default on the loan? Or?
Yeah, in this case, we're just looking at harm in terms of decreasing credit score.
Oh.
You can kind of think of this as, where the credit score basically represents all of your financial health, right? So I want to absorb like the harm that you're talking about into the credit score. Whether this is realistic is another issue. Yeah, so maybe this is just the first principle component of the harm. Yeah. So if I apply fairness constraints, just to recap what these are, so demographic parity is when I equalize the acceptance rate across two groups. And equality of opportunity is where I look at all the people who would repay. So I look at the people who are positives and want to make sure that I'm selecting the same fraction of positives for both groups. And then subject to these constraints, then I maximize the bank's utility. So the first result is that if I apply equal opportunity and demographic parity, I can cause any of the three delay impact regimes that I talked about just now. And what I mean is that given any two population distributions of scores, I can find settings, right, that where equal opportunity or demographic parity cause improvement harm or harm or active harm. So in contrast to that, unconstrained utility maximization can never cause active harm. And that's also because we assume that the bank's utility structure is such that it's more conservative, right? So this is a general result. There's somehow is sort of the most general thing you can say, which is that there is possibility that the fairness criteria will cause harm. So if we want to compare, in a more fine-grained manner, what the choice, how does the choice of different fairness criteria matter, we can also do that. So there is a class of settings we can find that demographic parity causes active or relative harm, whereas equal opportunity does not. And that's because demographic parity tends to over-accept, right, in a disadvantaged group, and it pushes the acceptance rate above utility maximization. And then in this class of settings, it ends up in the active harm region, whereas equal opportunity in the same class of settings is more conservative. And then you can also say, would this conservative aspect of equal opportunity cause harm? So that is also possible, but it will cause harm by under-acceptance. So in this other class of settings, you have equal opportunity actually accepting less than utility maximization, whereas demographic parity actually never under-accepts relative to utility maximization under any setting. So then there's also a possibility of this kind of difference, right, when we apply equal opportunity versus applying demographic parity. So the choice of fairness criteria matters. And then before this, we kind of talked about the situation where we assume the bank knows the mapping from credit score to repayment ability. But what if there's actually measurement error? So here we consider this particular type of measurement error where the bank systematically underestimates a group's repayment ability. So what this means is that the bank thinks that 700 equals the 0.8 probability of repaying the loan, and that holds true for the orange group. But for the blue group, people who are assigned, people who have a true probability of 0.8 of repaying their loan are actually assigned a lower credit score. So in this case, where there's systematic underestimation, how does the impact of fairness criteria change? Right, so first we can characterize this in a straightforward way, which is that the acceptance rate for a group is lower if their scores are systematically underestimated. Right, and this is still true even if we applied a fairness criteria. So now what is happening is, if I knew the true scores, then that's where my beta max util would be. But then if my scores are actually underestimated, my beta max util would be lower than what it would have been. And then for demographic parity, it tends to under-accept. So if I knew the true scores, that's where my demographic parity acceptance rate would be. But if I actually underestimated, then my demographic parity would be lower than the than if I had known the true scores. So now we see this interesting situation where the max utility acceptance rate under error is actually in this harm regime, whereas demographic parity by over-accepting corrects for the underestimation, right? So this could be a reason why, this could be an argument for why we want to use demographic parity, right? So it might be to correct for some measurement error that we believe is there. But then again, so it's possible that it undercorrects or overcorrects, right? So that is another issue that is not clear unless we actually have access to the distributions and can check whether this is true. So so I've talked about the theoretical results, and now we'll look at how this plays out with some real data. So we use some credit score data from that's actually publicly available from FICO. And what we did is we used the empirical data to estimate the group score distributions and the repayment probabilities. And here we just look at two race groups, white and black. So if we look at that graph there, and we recall that our assumption is that the scores are monotone within the repay probability. And this is actually true if we just look at the actual scores, right? So here we are kind of averaging over non-identical loans, right? So this is not exactly the setting that our theory was in, but then we just use that for now. And then there are some things that we cannot estimate from the data, right? And basically, it might even be very hard for economists to estimate, which is what is the bank's profit versus loss ratio, and what is the change when you're in your credit scores when you repay versus when you default. So we just have to choose certain parameters, and we say these are our model parameters. And in this case, notice that we have chosen the bank's profit-loss ratio to be more stringent than the delayed impact ratio, right? And that's because to fit with our assumption that the bank is more conservative, right? And it stands to lose more from a default than the individual. So using the things that we estimate from the data and our chosen model parameters, we can compute the outcome curves. And I mean, if you have a question, if the question is like, you know, how does this change with different model parameters, which is like these things do change. And we have a notebook online that accompanies the paper where you can play with these parameters. So if we just plotted the outcome curves for our chosen parameters and the data, you know, we see something like this. Already you can see that the outcome curves for the black group and the white group look very different. Right, so to remind you, the x-axis is the acceptance rate, so proportion of people we're accepting, and the y-axis is the score change, or what we call the delayed impact. So if we applied just utility maximization, in the bottom I'm plotting how the bank's profit changes with the acceptance rate, and we take the maxima of both curves, and that gives us these acceptance rates for the two groups, right? And in both cases, we see that when the score change is net positive, right? So if we applied demographic parity, now we are enforcing equal acceptance rates for both groups. And what has happened here is that now the black group is in the active harm regime, right? And you're drastically over-accepting with respect to the utility maximization acceptance rate. And if we change the fairness criteria by applying like equal opportunity, now again the black group is in the improvement regime. So what this example really shows is that there's a large difference in the delayed impact for the minority group. Whereas for the white group, whichever fairness criteria I choose, I'm always in this positive impact regime. But for the black group, we can see that the maxima of the utility curves, right, is very different from the maxima of the delayed impact curve, right? And this misalignment is what is pushing the acceptance threshold into different regimes on the delayed impact curve. So I'll just recap what I've said and what I've told you before, which is we propose this very simple tool called the outcome curve as a way to reason about how we should be deviating from profit maximization. Like if there is a particular outcome in our application that we care about, then we should be modeling that and then deviating from utility maximization in a way to improve the outcome, right? And that naturally leads to the issue of domain specificity of fairness, right? So if we applied a fairness criteria, typically that is, in fact, in general, that's just completely agnostic to the domain that you're working with. And a way to incorporate context, right, is by considering the outcome models in your application. So in future work, I think there are lots of great topics. For example, as the students pointed out, in this case, we're considering identical loans, right? And then this makes our decision space much simpler to reason about. Then the question is, when you move beyond binary decisions, do you get something more interesting, or what are the effects at play there? And also here we propose the mean score as a way to measure the impact, so as a way to measure how the group distribution has changed. But obviously that's not the only way. And now the question is, what are other meaningful ways of measuring the impact from these algorithmic decisions? And that was also a great direction. And then more generally, right, there has been a lot of work on looking at the dynamics of the distributional impact of machine learning algorithms. So there are some work that are looking at like feedback loops, right, that are present in predictive policing. And there are also some other work that look at dynamics of imposing fairness constraints in the labor market. And more recently, there's also some other work about looking at the demographics, how the demographics in your population changes when you apply certain fairness criteria. So there are many interesting questions at the intersection of dynamics and fairness and societal impact of machine learning. So yeah, so I hope that that gives you a good overview of some of the questions that we're thinking about. And yeah, thank you for listening. Yes?
Oh, so it struck me a few times that the problems you're grappling with look pretty similar to problems in causal inference. Like when you had your, let's see, when you had your sort of confounding variable or your group defining variable. I'm sorry, no, it wasn't that. It was the credit score itself. The credit score might condition the probability of the loan. And that looks like a pretty traditional confounding variable that you could use a propensity score or something to correct for. In other words, the strata by that variable, if you just measure your effect within each stratum, in theory, that variable kind of goes away. And more generally,
you're saying that the credit score could confound the outcome of
the credit score, yeah, I think both questions were asking along those lines. But even if it does, that's a kind of a known kind of confounding. If you have a linear model of that effect, you can normally compute the effect.
Yeah.
And then what's left over should be independent of that effect.
Yeah, yeah.
And that sort of suggests that I wonder how many of these problems persist if you use standard causal inference methods where you do, say, matching, and you take an instance from group B, an instance from group A, try to pair them up, which might be many to one. But still, you're getting, in a sense, pairs that have the most similar attributes. It seems like that would at least maybe deal with some of these issues under some assumptions that.
Yeah, I guess so. If you applied this like correcting for confounders method, so if you're trying, right,
I did two different questions. One of them is correcting for
it would give you a better credit score in a sense. Yeah.
The other method is to try to measure a sort of an unbiased causal effect, where basically you have two prototypes that just differ in the actual conditioning variable, or let's see, the classification, the X variable that you like to measure, but they say they have different values of A, but the populations with different values of A can have different distributions of X.
Yeah.
But if you pair them, then basically you're normalizing.
Right.
Finding a very similar X that differs only in A.
Right. So you condition on the features.
That removes some of the distributional biases between populations.
Yeah.
Curious if you could provably show that reduces or eliminates some of these types of bias.
Yeah, I think there's some work that's related to that about like there are a couple of papers about counterfactual fairness, and I think, yeah, I'm not sure what I would say is the connection to this, because I guess in general, so what we are concerned about in this paper is when you apply a fairness criteria, right? Even supposing that you have a very good score that corrects for these confounders, if you just apply a fairness criteria naively, there's no way you can really account for the harm structure in that problem, right? So there are, so maybe if we had a better score, then we can say like the situation of harm is like, has a smaller likelihood under a certain model, but doesn't eliminate that completely.
It actually corresponds to your last criterion, because it does actually measure, it should be independent condition on a given x, because once you fix x, you're basically doing matching. So I think it would probably have that kind of fairness. But if that's, you know, if you want a different fairness criterion, then you'd need to do something else. It's just,
yeah, I have to think about that, yes.
Yeah, I'm curious about what would happen if you change the, I guess, profit and loss function for the bank or whatever, such that it's not that they win whenever the you know, the borrower wins and they lose whenever the borrower loses, like where a bank can end up, you know, in the real world, you know, a bank can end up still making a profit if they collect a lot of interest and then the borrower defaults and they're able to possess the principal, like the house. Like in that case, wouldn't you be able to have a utility maximization scheme that produces a very bad outcome for where, you know, people, the bank will lend, you know, with the intention of, you know, enticing people to default and reclaiming the asset. Is that?
Yeah, that's true.
Does that show up if you just change in your framework, if you just, you know, change the loss function, or is there more, I guess, gymnastics involved? So basically, it's kind of an obvious consequence of the model, right? So if you have, if we change the structure such that the bank is incentivized to give out like more bad loans, like maybe this is reasonable in like a subprime loan setting, then it basically falls out that from the model that my beta max util could be causing active harm, right? So that would be, I mean, isn't that? I don't think there are more gymnastics involved. That, I mean, I would argue that's more realistic, I guess. So I guess maybe the question is when you have the reversal of that, you know, when the bank is not conservative but has an incentive to give out more bad loans, then you just change sort of the regions that we're arguing about, right? But then this conclusion that fairness constraints like can put us in any region is still the same, right? But then maybe given you have to characterize the regions for differently, but then the general message is, I don't think that would change. I had another question. You had the plots of, I guess you had the plots of like default rates versus, or what was it? I think it said like, you had the plots like the black plot for the plot for black people. I think what was it, acceptance rate versus mean credit score. Like these guys. Right. No, forward. I mean. This one? The next slide, I think. Yeah. So are these are coming from the data, and are these? But these are so these are coming from the FICO data, you're saying? Yes. So what's coming from the FICO data is the repayment probabilities and the corresponding scores. So this is coming from the FICO data as well as the relative size of the group. How is FICO? Wait, where does the repayment probability come from? The repayment probability, so we know the repayment, so this is after some kind of binning, right? So we have to, so what FICO has is like the repayment outcome, which would be 0 or 1, right, for each particular score. And then you bin the scores and then you average
the outcomes right in
Okay.
that bin.
So these are calculated empirically.
Yeah, yeah. So this is the empirical part of the data.
But isn't this contingent? Isn't this conditional on these people receiving a loan, and so therefore not a measurement of the repayment probability, but the repayment probability conditioned on the bank deciding to extend them a loan?
Yeah, I think that's a fair statement. But basically, we don't have the counterfactuals. So this one is what we're going to use as the function that's mapping from score to repayment.
What are the implications if this is, if I guess you're, instead of measuring the population, when you're assuming you're measuring the population, you're measuring, you know, like some subset that might be different in, yeah, I mean, like, I guess I'm thinking, you know, like, if you're already, yeah, I guess I don't.
So I guess you're saying that the fact that we give them a loan might be a confounder for the repayment probability, that people you give a loan to might have like higher repayment probability compared to people with the same score who did not get the loan or something.
I don't mean that. Well, the FICO score is supposed to be, you know, like the people with the same score, the same repayment probability.
Yeah.
But, I guess so. Why? Well, I guess here's one question: like, why is it that just in this data, if we're assuming that the FICO score is a factor, I mean, is a good proxy for repayment probability, that the black curve is just, you know, strictly below the white curve?
Yeah. So I think I wouldn't read too much into that because. First, like if I were to plot the confidence intervals based on the amount of data, I have the two curves actually overlapping.
Oh.
So statistically, you know, I may not be able to argue that the two of the repayment probabilities are significantly different.
Okay.
Yeah.
I guess I would be interested to see, like, you know, we were talking about conditionals, you know, conditional, like you're saying conditional on C equals Y kind of thing, like,
Yeah.
that made me, you know, at the beginning of the talk, that made me recall that, you know, where this data set is conditional on C equals Y, or on the choice is, like the conditionals are just a little bit,
right, it's true that it's conditioning on C equals 1, that they have gotten a loan. Yeah. Yeah.
So I guess if there were confounding variables in, you know, loan decisions beyond like whether we think they can repay it, that would be hidden in this data set.
Yeah, yeah. I think that is fair to say in general. Then whether there is an effect, you have to actually maybe collect more data to see if there is an effect here.
Okay.
Yeah. Yeah.
You know, have you thought about how to do that?
Yeah, that's not something that I've thought of for this problem specifically.
Is it in another context, or?
Yeah, I guess the question, I think what you're asking is like the question in causal inference, right? Like given that we don't observe.
Sure.
Yeah, so yeah, I don't really have a good answer right now for that. Yeah.
Any other questions? All right.
Okay.
Thanks
Yeah.
for the,
Thank you.